Hello, today we're looking at section and topic 7.1, area of a region between two curves. So this begins our last unit of study, applications of integration. So we have two concepts that we're going to be looking at. We're going to be looking at area and we're going to be looking at volume. We have broken the volume down into 2 days. One where we're going to rotate the curve around an axis to create a 3D shape. And two, we're going to use what we have and start as a solid or a base and then build area up, accumulating the area as we go. All right, so the first piece we're looking at is area between two curves. So when we look at this area, we're going to be talking about definite boundaries because as you look at this graph f of x, it has a definite boundary here at 1 and a definite boundary here at 3. So what we're talking about is this shaded area that's between the two boundaries, so definite integral. So if we were going to write the definite integral for this first shape, then we would have our integral sign and our boundaries would go from 1 to 3. The name of the function is f of x, and then our variable of integration at the end would be dx. All right, so let's look at our second shape. So again, we can see that we have definite boundaries here at 1 and here at 3. The name of this shape is g of x, and we can't just use geometry shapes or things like that to find these areas because this has a curve at the top. It's not just a square or a rectangle or some geometric shape that we use. We have a curve here, so we don't have any kind of geometry shaped or formula that we can use to produce that. So let's do our area, which is our integration is finding the area. And so our boundaries again are going to go from 1 to 3. The name of the function is g of x, and then our variable is dx. Okay, so what we're going to do on the third shape to find area 3, we're going to take the first shape that went from the top all the way down to the horizontal axis, and we're going to subtract the second shape, which started here at the bottom and went to the horizontal axis. So we're getting rid of this piece right here. So hopefully you can see, if I superimpose over here, that when we have the whole shape like area 1, and then we take away the second shape, which is area 2, then we're left with this piece. Now we still have those definite boundaries that are going from 1 to 3, but we're going to be subtracting out that second area. So when we set this up, remember we're going to take area 1 here, and we're going to subtract area 2 here, and that's going to leave me with area 3. So that's the process that we're doing. So we already have our intervals set up. So we're going to come over here and say the first integral, which goes from 1 to 3. And that's f of x dx. And then we're going to subtract the second interval, which is going to be integral from 1 to 3 of g of x dx. And so we know from our integral properties that when we are subtracting with the same boundaries, that we could also write this as the integral from 1 to 3. And I'm going to put brackets so I can remember that I'm going to take the first function minus the second function, close that out, and then have my variable of integration on the back. And so that's where this area under the curve that we're finding right here comes into play. So if we have a function f and g that are continuous on a closed interval, g of x is less than f of x, and it's bounded by vertical lines a and b, so it's bounded right here and right here, then the area can be found by this integration. So we'll be using that concept in today's lesson. All right, so here is a list of steps, and I will tell you up front, I don't always do them in this order, but I do all of the pieces of this. So to find the area under the curve that we've been talking about, this is just kind of an organized list of what we were doing. So we're going to sketch and draw a graph. So if we don't have a graph like we did in the first part, then we're going to sketch the graph. And we're going to find any necessary information. I tend to label the function, all of that fun stuff. Then we're going to determine whether we're going to use a dx situation or a dy, and we will determine that by looking at the equations themselves and determining what are they in terms of. Is it x in terms of y or y in terms of x? Then we are going to find the limits from the boundaries. So that could be the axis, that could be intersection points. We're going to set up an integral, and it's either going to be top to bottom if it's dx or right to left if it's dy. And then we're going to integrate the statements, the area statements that we found, evaluate it using the fundamental theorem, and come to our answer. Okay, so that is the process that we're looking for. So in these first problems, notice that we are not going to be using a calculator. Okay, so some of these we're just going to set up and safe stop. Some of them we will actually work out so you can practice doing both. All right, so let's look at problem 1. So problem 1, it says find the area of the region bounded by the graph of y equals this and y equals that, and x equals this and x equals that. So that's my first read, just getting my general idea of what's going on in the problem. My second read, then I can see that I'm finding the area, and since I'm doing this process, that's either going to be geometry formulas or it's going to be integration because I have to find area. It tells me that it's bounded, so I know that I'm going to have definite integrals. And then I can see that I have one equation here, a second equation here, and some vertical boundaries here. So the first thing that I always do in a problem like this is I don't like it that I have two y equals equations. I think it's harder to keep straight. So I usually start by identifying that I'm going to use f of x to be the y equals equation for x squared plus 2. And then I'm going to use g of x to be the equation for the y equals negative x. It's much easier to keep my functions straight if I have them named. So the next thing I'm going to do is I'm going to graph them. So this is just a quadratic that opens up and shifts up 2. So I'm going to go up 2, over 1, up 1, over 1, up 1. And so I'm going to get this quadratic that's going like this. And then the other one is a line that has a negative slope. So I'm down here. Turn this sideways so I can draw the line real quick, guys. Okay, and so this one right here is my g of x, and this one right here is my f of x. And then I have vertical lines at 0, and I have a vertical line at 1. So then that means the area that I'm trying to find is between the curves and the vertical line. So we're talking about that area. That is the area of the shape that I'm trying to find in this problem. So notice that it does have some area below the horizontal axis, but because we're going to be using the fundamental theorem, that will take care of itself as I'm working through the problem. All right, the next thing I want to do is look at the equations themselves. So I am going to ask myself the first question. When I ask myself this, I always say in terms of what? And what that means is when I look at this equation, you can see in it's x or y is in terms of x. Y is in terms of x. So I'm going to say it's in terms of x. When it's in terms of x, then I'm going to be using a dx situation. And if it's dx, then it's going to be top minus bottom. Now, where does all that come from? All right, let's go back up to the steps. So we're going to sketch and draw. We're going to determine if we're going to use a dy or dx situation. We're going to determine the limits or the boundaries. Then we're going to set up an integral based on is it top to bottom when it's dx or is it right to left because it's dy, and then integrate. So I'm kind of a visual person, as you guys are well aware. So we're going to come up in this space right here and write a couple of visual statements that will help us. So if we decide it's in terms of x, then that's going to be a dx situation. So your boundaries are going to be x left and x right. And then in here in your integral, it's going to be top minus bottom. And it will be a dx situation. If it is in terms of y, then we're going to use y bottom, and we're going to use y top, and then inside it's going to be right minus left and a dy situation. Okay, so that's why I start out when I'm working my problem is asking myself these questions. It's in terms of what? And it's x, so it's in terms of x, which means it's going to be dx situation, which means since it's a dx situation, then I'm going to be doing top minus bottom. Okay, so when I have these areas, sometimes it's helpful when you're doing top minus bottom or right minus left to make sure when you're labeling these, I'm going to actually move my label of f of x down here and g of x down here so I can look at the area itself and I can clearly see this is the f of x, this is the g of x. You don't have to, just a suggestion. All right, so now that we have this, we're going to go about setting up our intervals. So we know we're using a dx, so we know we're using this situation for the problem. So I'm going to set up my intervals that are going to go from 0 to 1. And we're going to do f of x minus g of x, so top minus bottom. So I'm going to come in here and I think I'll set this up with the boxes here. So I'm going to do f of x because that's what's on top minus g of x because that's what's on bottom, and then it's a dx situation. So that's my setup that I'm going to use. Now I'm going to go ahead and take care of the information inside. I can do this in one combined statement. Remember up here we did it in two separate statements. You could do it like that. And I'm going to do it in this kind of situation if I don't have the same boundaries, if I need to use sub on one part of it and not the other, things like that. But these are just basic quadratic and linear, so I can do it in one step. So I'm going to say the integral from 0 to 1, and then inside here, I'm going to put in my f of x function, which is x squared plus 2, subtracting my g of x function, which is negative x, and then I have a dx situation. Don't forget to drop that dx when you're supposed to and not too early. All right, so let's clean up the inside just a little bit. So I'm going to go from 0 to 1, and inside then I have an x squared. I have a negative times a negative, so I have a positive x. And then I have a positive 2. And so once I get it cleaned up, then that becomes a very easy problem to integrate. So I'm going to come up here. So I'm going to be integrating this. So I'm going to be finding the antiderivatives and then using my fundamental theorem of calculus to evaluate it from 0 to 1 as we've been practicing. Okay, so let's start by finding the antiderivative. So when I find the antiderivative of x squared, I get 1/3 x cubed. When I find the antiderivative of x, I get plus 1/2 x squared. When I find the antiderivative of 2, I get plus 2x. And then I'm going to evaluate that from 0 to 1. Okay, so when I am doing my evaluation here, then I'm going to plug in the top bound minus the bottom bound because that's the fundamental theorem. So I'm going to plug in a 1 for the x cubed and I get 1/3 plus, and when I plug in a 1 for the x squared, I get 1/2 plus, when I plug in a 1 for the x, I get 2. Then I'm going to subtract when I plug in 0, which is just going to 0 plus 0 plus 0. And so, yeah, I do write that on my paper just so I have it as part of my process. This would be an okay safe stop at this point if you didn't need this answer for anything else in the problem. If you did need this answer for anything else in the problem, then you would go ahead and calculate it. We're going to go ahead and calculate it just for good old-fashioned practice. So when I have these problems right here, I need to get a common denominator, so I'm going to make them all 6. So that's going to be 2/6 plus 3/6 plus 12/6. And then when I crunch those numbers, 12 plus 3 plus 2 is going to give me 17/6. And so that's how we'll tackle our problems for today. Okay, so the next problem we're going to look at is when we're finding area between the curves, but they are actually intersecting curves. So right here we had vertical lines that defined our boundaries. In this case, we're going to be looking for area where they intersect. So that's going to look more, like if we use this example here, but we were going from that intersection to this intersection and finding all of this area. So that's what this problem is going to be like. So our first read, find the area of the region bounded by the graph of f of x and g of x. And that's it. Notice it doesn't have any vertical line bounds. So again, we're finding area, so we know we're going to integrate. Again, it states that it's bounded, so we know it's a definite integral. And then we have an equation that's already defined f of x and g of x. So it's not like this one where they are both y, and I was trying to keep them straight. I can actually just go with the notation that they have. So remember we said the first thing we're going to do is graph. So we're going to graph this one, which is a quadratic turned upside down and then shifted up 2. So over 1, down 1, over 1, down 1, over 2, down 1, 2, 3, 4. 2 down 1, 2, 3, 4. All your mad graphing skills from Algebra 2 and Pre-Cal should be coming back here. All right, so this is my first function, which is f of x. And then I'm going to graph g of x, which is just a positive slope. So starting here, I'm going to go here, I'm going to go here, I'm going to go here. Let me turn this so I can connect those. And we have our graph. Okay, so what is it we're trying to find the area of? We're trying to find the area between the curves from each intersection point. So this is the area that we're looking for. So I'm looking at this area, and when I label this, I know the upside down graph is going to be my f of x, and I know the straight line is going to be my g of x. So I have those values. And then the next thing I want to know is, can I find the points of intersection from the graph? If I can, awesome. And I can right here. Excuse me, right here I can see that's a 1, 1. So that intersection point is 1, 1. And here I can see that's negative 2, negative 2. So I've gotten the information I need off the graph. I know the area I'm looking for. I know where those intersection boundaries are. I can see this graph is here and this graph is here on the picture. So remember my questions. I'm asking myself, in terms of what? Is this equation y in terms of x or x in terms of y? So it's x in terms of y. And if it's x in terms of y, then it's going to be a dx graph. And if it's a dx graph, remember we said it was going to be top minus bottom. So those are all the things that I would do before I started the problem. And that's kind of taking me through sketching the graph, determining which one it is, making note of which way I'm going to set up the integral, figuring out what the boundaries were. So it may not be in that exact order, but it's all of the things in that list. So now we're going to go to setting up the integral. So I'm going to say my integral is going to go from, and since we said it was x, so it's a dx situation, then I'm going to go x left, x right when I'm writing this integral. I'm going to down here, and so my x left is negative 2, so x left here, and then 1 is my upper bound. Then I'm going to do top minus bottom, so f of x is on the top, g of x is on the bottom. And then I have my dx because we said it was going to be a dx situation. All right, so let's clean this up so we can integrate. So we're going from negative 2 to 1, and I'm going to put in my f of x function, which is 2 minus x squared, and then I'm going to subtract the g of x function, so I'm going to subtract x, and then I have my dx. I haven't integrated, so that notation is still there. So now I'm just going to kind of clean it up. I'm going from negative 2 to 1. And so inside here, I have a negative x squared, a minus x, and a plus 2, and it's dx. All right, so now we should be able to integrate without any trouble at this point. So when I find the antiderivative of negative x squared, I get negative 1/3 x cubed. When I find the antiderivative of negative 1, I get negative 1/2 x squared. When I find the antiderivative of 2, I get plus 2x, and I'm going to evaluate it from -2 to 0. So at this point now, I'm applying my fundamental theorem of calculus. So when I apply my fundamental theorem of calculus, then I'm plugging in the upper bound, and I set my boundaries up wrong. Sorry about that, guys. Give me just a second to fix this, because that didn't make a whole lot of sense. All right, so I am going from -2 to 1, not 0. So I'm going to plug in the 1 to all of this, subtract, plug in the -2 to all of this. So as I do the first part, and I plug in a 1 here, I get -1/3. When I plug in a 1 here, I get -1/2. When I plug in a 1 here, I get 2. Now I'm going to plug in a -2. And so I do -2 cubed, which gives me -8. -8 times -1/3 gives me +8/3. And then I plug in -2 in here, I square it. So then I'm just going to get -2. And when I plug in a -2 in here, I'm going to get -4. All right, so if we were able to safe stop, we would do it right here. If it's a multiple choice question, then you would get a common denominator for this side, get a common denominator for this side, put these two sides together, get an overall common denominator, subtract this from this. Okay, so we're just getting to that point today, so we can make sure we get through all the problems. All right, let's move on. So our first retest, we're finding the area of the region between the graphs of f of x and g of x. So it's identified as specific graphs, so that works for me. This did wrap around here, so make sure that you see that that's plus 2x as part of that whole equation. So my second read is we're finding the area, and we know it's bounded, so we're having a definite integral. We know that we have this right here, and we know that that's cubic. And we have this equation here, and we know that that's quadratic. So as we look at the nature of these two functions, we can think about behaviors. A cubic function can bend and go back in the other direction. A quadratic cannot. So as I'm looking at my graph, then because the cubic can go back the other way, it can have more than one area that we might be talking about. If we have more than one area that we might be talking about, then that means we're going to have to do our process more than one time. So I'm going to set it up and solve for this area, and I'm going to set it up and solve for this area. So for purposes of this problem, we're just going to call this area 1 and area 2. So since the nature of the cubic function is it can bend and move back around, I want to be very careful in what function I'm talking about. So for instance, we kind of got that set up. I can see intersection points here. I can see a clear intersection point here. I can see a clear intersection point there. So now that we have everything labeled here, I am going to pay attention to the fact that my cubic function is f of x. So right here, f of x is on top, and in this area, g of x is on bottom. But over here in this area, g of x is on top, and f of x is on bottom. So I like to mark those to help me keep track. The next thing I'm going to do is answer my question. So in terms, what is the equation in terms of? And it's in terms of x, which means I'm going to use a dx situation, which means I'm going to set my problem up top minus bottom. Okay, so there's my setup information. So now we're going to go into the problem. This one we're just going to set up only so we can practice all of our other ones, okay? So we're going to set this up, and we have two areas, and then we're going to add them together. Okay, so let's start with area 1 first. So we're going to look for, remember our statement over here, if it's top minus bottom, so we're going to do x left, x right, top minus bottom. So x left is going to be -2 of just area 1, and x right is going to be 2, and then inside here we're going to have top minus bottom of that region, and then I have a dx. So that's just this part right here. Now I'm going to add to that this area right here. So it is still in terms of x. So we're going to do our x left, x right. So here's my integral, but now our x left goes from here to here. So it's going to go from 0 to 2, and then I'm top minus bottom. So over here on top now, remember, is g of x. So it's going to be g of x minus f of x, close that in, and our variable is dx. And so this is my setup only for this problem. As you can see now, I'm going to, if I were to work it out, I would put my functions in here. I would figure out what my inside is. I would find the antiderivative and evaluate it from -2 to 0. And then I would put my functions in here. I would find the antiderivative. I would evaluate this one from 0 to 2. And then I would add all of that up at the end. All right, example 4, we're going to set up and solve so we can practice some solving again. But I want you to look at it and see if you can tell what's different from the previous ones that we did. Hopefully you can see this is x equals in terms of y, so it's y in terms of x, y in terms of x. Well, again, now I have two x equals, and that's not super conducive to keeping our information straight. So I'm going to reassign them letters, and I'm going to say f of y, because remember, it's y in terms of x, equals 3 minus y squared. And then I'm going to do g of y, and that's going to be the second equation, which is y plus 1. So I'm going to start out identifying that. Now I'm going to go over here to my shape, and I can see that what I'm doing is finding this part right here. That's the area bounded by the intersections. So when I look at my shaded area right here, then I am looking at this intersection point right here, which is 2, 1. And I'm looking at this intersection point here, which is at -1, -2. And then I'm paying attention to the fact that this curve, this sideways parabola, is my f at y, and the straight line is my g at y. So of this shaded area, this is the one that's to this side and this is the other. So I'm just identifying that information. Now I'm going to ask myself my questions. So in terms, it is y in terms of x. And if it's y, then it's going to be a dy situation. So if we go back to page 1, when it's a dy situation, it's going to be y bottom minus y top, and inside here is going to be right minus left. So my answer this time is right minus left. So now I'm going to set up my integrals. So for this particular one, remember it's going to be y bottom, y top. So y bottom, y top means my boundaries are going to go from -2 up to +1, and it is right minus left. So in here, this is the function that's to the right of the other one. So here minus here. So then that's going to be f at y minus g at y. And it's a dy situation this time instead of a dx. So right minus left, y bottom, y top. All right, so let's go ahead, and I'm going to have you pause your video and plug in all your information, find your antiderivative, and use the fundamental theorem to evaluate it to get your answer. Pause your video. Well, how did you do? So we collected our like terms here, we integrated here, applied the fundamental theorem, got this, cleaned it up, put it together. I got 9/2, and we don't have any units for this particular problem, so we are good to go. All right, let's look at 5, and then we're going to switch gears and do a couple little calculator things, and then we will be finished, guys. So first off, I'm going to come over here to my graph, and I know that the region bounded between the two curves is this part right here. That's region R. All right, and I'm going to do my reads now. So when I look at this, I've got a function f, I've got a function v, r is the region bounded by the graphs shown. And then we're going to do a couple of things. So first off, we have them designated with their own letters, so I don't have to reassign anything. I know that I'm talking about the R region that's bounded, so I know I'm talking definite intervals. All right, but notice that the first part of this, it's asking you to write the equation of a tangent line. What do you need to know to be able to write the equation of a tangent line? You need to know the point and the slope. Okay, we've been doing this since the second unit of school, so this should not be a difficult challenge. Then when you get to part B, you are going to proceed, to do what we did today and to find the area under the curve. So I'm going to come over here and label some things before I have you pause your video again. And I notice that we have the intersection point here of 0, 4. I know that I have an intersection point here of 2, 0, so I have my intersection boundaries. I know that this is the quadratic part of the equation, so this side is going to be f of x. And I know that this side is going to be my part of my transcendental function, my cosine function, so this is going to be my g of x. So then when you get to part B, don't forget to ask yourself the questions in terms of what, and then make your statements like we've been doing each time here, and then find the area. So pause your video and see how you do with this part of a FRQ. Pause now. All right, so check your work and make sure when you did this side, you needed your U sub, and we got your U sub, that's 16 pi, so there was 4 out there, and then 4 over pi, so you get 16 pi. That one just, that coefficient just applies to this first derivative, because we're going to integrate with respect to U. We need to be sure we remember to change our boundaries, so I went from 0 to 0 and 2 to pi over 2. And then we found the antiderivative and evaluated, antiderivative and evaluated, collect like terms, and set you're safe stopping somewhere in there. We're going to go ahead and safe stop just for time's sake today. We're going to switch gears now, and these last two questions we're going to practice doing these problems on the calculator. So if you don't have your calculator, run and pause the video and run and grab it real quick so that you can practice along with me on these two. Just because it's a calculator problem doesn't mean that you don't have to put your work down. So we're going to go through what I would expect to see on your paper and run through the calculators real quick. So pause your video if you need to go run and grab your calculator. If not, away we go. So as we're looking for the first read here, we see find the area. So we know where you're doing integration. We know it's going to be a definite interval. We have the first function in terms of f of x and the second one in terms of g of x, so I don't need to change any boundaries. So then I'm asking myself my questions. So in terms, what is it in terms of? It's in terms of x, so that means we're in a dx situation, so we're doing top minus bottom. I always want to do that before I start so I know where I'm trying to go within the problem. All right, so now as we go to our calculator, what is it we're putting in the calculator? So in my y1, I'm going to enter my f of x function, and in my y2, I'm going to enter my g of x function. So I'm going to take my calculator in y1, I'm going to put negative x squared plus 4x plus 1. And in my y2, I'm going to put e to that, and I'm going to make it look just like it does on my paper. So I'm going to get my fraction template. And I know, on the test in May, you do have access to Desmos, but I think there are some things that are easier in the calculator, and this to me is one of them. So that's why we're going to practice it this way. All right, so we put our equations in y1 and y2. I double checked my equations, negative x squared plus 4x plus 1, and e to the 1/2 x minus 2. And that's what I just said I was doing right here. So the next thing we're going to do is go to our graph. And, whoops, I don't know what zoom I just did, but that's not the one I wanted. So let's go in here and do zoom 6. And we'll start with just a basic graph, and then if we need to adjust the window to see the intersections, we can do that. But I think this is probably going to work, and it's going to give us this picture. So I am just going to rough sketch this onto my paper, so you can pause your video while you do that. So here's my picture that I just rough sketched from my calculator. So I didn't try and put axis or anything. I'm just kind of looking at the information I need. So I know this is my bounded region. I know I'm going to go from here to here. And because I'm talking about two intersection points, I'm going to have to store two separate types of values. I'm going to call the point over here, the first one I calculate, AC. And then I'm going to call the point over here BD. And I am going to go ahead at this point and store X and Y for each of these intersections. And the reason is, if I need it, I have it. If I need it for later on in the problem, I still have it, and I don't have to go back and recalculate. Sometimes you may not need those Y values, and that's okay. But if I already have it, then I don't have to worry about needing it later and not having it. And then I've got to go back up in my problem. I've got to reorient myself to that part of the problem. I've got to get what I need from that part of the problem. Then I have to go back to where I'm working and finish what I was working to start with. So it just saves us a little time. So I'm just always in the habit. So how I'm going to do this is I'm going to find these. I'm temporarily storing them in my calculator as I do the intersection tool. And then I'm going to say the first X is going to store in A and the first Y is going to store in C. So this is the first one, and I just am creature habit, so I'm going to do it that way. And then the second one, I'm going to say the new X is going to store in B and the new Y is going to store in D. And this is going to be for my second point, which is over here. All right, once I have that, then I'm just going to set up the integral. So my integral then is going to be, the questions were in terms of X, so top minus bottom. So that means I need X left, X right. And so my X left is going to be A, my X right is going to be B, and then I'm going to be doing Y1 minus Y2 with the variable of integration of dx. Okay, so now let's go to our calculator and do all the stuff that we need to do. Okay, so let's move it so you can see. I think we're okay here. All right, so I have my graph. So I'm going to do second trace, which is where our intersection tool is. We've learned to use in Algebra 1, Algebra 2, and in Pre-Cal. We did it again. So then I'm going to move my cursor over close to the intersection on the left. I'm going to hit enter 3 times, and I'm going to wait until I see the words intersection down here on my calculator. Right now, your calculator has temporarily stored that X value in X and that Y value in Y. But the minute we do the next intersection over here, it's going to erase it out and store over it. So I want to take this intersection and put it in my calculator for later use. So without here and hitting clear or anything right now, I'm going to do second quit, or that's the second mode button. I'm going to type in X. I'm going to press the store button, which is right above on, and I'm going to do alpha A. And when I hit enter, that number that was just on my graph is now stored in my A, so I can use that in my home screen. Then I'm going to do Y. To get Y, you do alpha, and Y is right here off the 1 key. And I am going to store that in alpha C and hit enter. All right, so far now I have my X and my Y from the first intersection. So now I'm going to go back to my graph. I'm going to do second trace intersection one more time, but this time I'm going to move my cursor over closer to where the other intersection is. I'm going to hit enter 3 times because I only have 2 things in my calculator. Once I see that the intersection word is there, then I'm going to do second quit, or do second mode, and then I'm going to once again say X, store it, but this time I'm putting it in B. So I'm going to do alpha B, and then I'm going to get my Y again. So I'm going to do alpha Y, which is down here off the 1 button, and then I'm going to press store again, and then I'm going to do alpha D. And so now I have all 4 values of X's and Y's stored. I can use them at any point I want to in this problem later on. So if there's a part of a FRQ where you might need that information in part C or D, you already have it stored. If you don't need it, it's no big deal. But if you do need it, you'll have it there. All right, so now I'm literally going to type this in my calculator. So I'm going to do alpha window, and I'm going to pick the integration, which is number 4. I'm going to do my boundaries because remember we did X left, X right. So I'm going to do from A to B, and I'm going to do alpha A. Then I'm going to go up and do alpha B. Then I'm going to go over here. Notice the parentheses are there, so we just have to put what's inside. And I'm going to do alpha trace, and I'm going to pick y1. Oh, excuse me. I got a matrix. Let's try that again. Alpha window, and I'm going to pick number 4. And then I'm going to do alpha A to alpha B, and I'm going to pay attention when I pick the right function this time. And I'm going to do alpha trace, and I'm going to pick choice 1 for y1 minus, and then I'm going to do it again, alpha trace, and I'm going to pick choice 2 for y2. I'm going to get out of my parentheses and put my X in for my variation. So I just entered this in my home screen. So when I hit enter, it's going to calculate that for me. And that tells me that my area is approximately 11.804. Oh, I'm off the screen because I have my calculator up there. Sorry. 11.804. And I'm going to go out to 3 decimal places. There are no units in the problem, so I don't need any units in my answer. All right, so pause your video one last time, and you are going to go through the process we just did for 7. We'll come back and compare answers, and then we will be through with this lesson. So pause your video. All right, let's see how you did. So we put y1 to be f of x, y2 to be g of x. When I graphed on my calculator, I got a picture that looks something like this, where the line here, the linear part, is my y2, and the curved part is my y1, and then I'm going from point AC to the intersection of point BD. So I stored x in A, y in C, x in B, y in D. I set up my interval. Remember, we said that it was in terms of x, which is dx, so it's top minus bottom. So that means I need x left, x right. So x left is A, x right is B. I am subtracting top minus bottom, so it's y2 minus y1. Don't forget your variable dx. And then I used my second window integration feature and found that the area is approximately 22.340. All right, so we had some by hands, we had some that we just set up and safe stopped, and then we had a couple of calculator practice at the end. So this is the stuff that you need to know right now about area under the curve. So make sure we have, all of our stuff down. We know how to use the steps. We know how to set up the integrals. We know how to ask ourselves the questions, so that helps us get things set up correctly. And then next lesson, we're going to delve into the volume things for this unit. All right, guys, be sure you do your check for understanding worksheet practice so you'll know if you have any questions for me when we come back. Thanks, guys. Bye.